Today we're going to look at various types of telescopes, how they work, and the different types of information they can give us about objects in space. There are two major types of telescopes that use visible light, reflectors and refractors. There are several other types as well, but these are pretty much just combinations made up of parts of the other two types. Refractors use only lenses. They use a large lens at the front of a telescope to collect and focus light. Reflectors use mirrors to focus the light by bouncing it off a curved mirror. There is no lens at the front of the telescope. Light enters the scope, bounces off the curved mirror in the back, and then bounces again off a secondary mirror to be collected into the eyepiece. Eyepiece lenses magnify the focused image and are found in both types of telescopes. Galileo's telescope was a refractor. Larger lenses make better telescopes, but they're also heavy and difficult to support. In this first image, you can see a huge refracting telescope. Making the lens bigger gives you a huge and rather unwieldy instrument pretty quickly. Newton's telescope was a reflector, and it was a big improvement on the refractor. A better instrument in a smaller size. When asked, many people say that telescopes make things appear bigger, but that is incorrect. That's what a microscope does. The things we look at in astronomy aren't small, they're just very distant. They make far-off things appear closer by magnifying the image. Magnifying power isn't the most important, though. The amount of light that a telescope can collect is what makes a telescope better or worse. Ideally, you want a clear, sharp image to look at in the sky. Many types of telescopes collect not only the light that is visible to our eyes, but also collect light from other parts of the electromagnetic spectrum. We can analyze this light to gain information about the objects we look at. Many telescopes are even equipped with digital cameras to take images as well. Think about what your eyes do when you cross from a well-lit area into a dark one or vice versa. Your pupils change diameter, either to allow in more light if it's dark or to restrict light if it's very bright. Telescopes that are narrow in diameter, like your eye during the day, cannot collect as much light as wide diameter telescopes. But any telescope can collect a lot more light than just your eyes. A telescope is identified by its diameter. My big telescope is a 14-inch. It's about 6 feet tall, but it's 14 inches in diameter. I also have 6-inch and 3-inch telescopes, and they are not nearly as good if I'm trying to look at a faint object. Telescopes are often called light buckets. The more light you can collect in your bucket, the better you can see. Here is an image collected with a small diameter telescope. Take a look at the details. Look at the sizes and brightness of the objects. I'm going to show you the same area of the sky next, but this time with a larger diameter telescope, and I'd like you to compare the images. It's easy to see a marked increase in the brightness of the objects. You can even see objects in this image that were invisible in the first because they were so faint that the telescope didn't even pick them up. Early reflecting telescopes had only one primary mirror. Since the only way to collect more light is to have a larger diameter mirrors, large telescopes are in demand. It's difficult to make a very high quality large mirror, so newer reflectors are often made of several smaller mirrors. Some, like the James Webb Space Telescope, are even built in these hexagonal honeycomb shapes. These are the two equations that go with this chapter. and you'll have to be able to use both of them on your exam. The first is a comparison of light gathering power. Simply divide the diameters of the telescopes and square the answer. This tells you how much more light gathering power the big one has compared to the smaller one. In the first example, you might initially assume that a 12-inch telescope is twice as good as a 6-inch telescope because the number is twice as high. But let's look at why that's not the case. I'd have to put two 6-inch mirrors side by side to make it 12 inches across, and the same thing going down. My 12-inch mirror is actually 4 6-inch mirrors stuck together, 4 times as good. The second equation is related to magnification power. For this one, divide the focal length of the primary mirror by the focal length of the eyepiece. This tells you how many times better you are able to see with the telescope than without. Larger mirrors not only improve the light gathering capability, but it also makes images sharper. Look how well defined the individual stars are and how crisp their nebulosity is. Nebulosity is what we call that blurry, gassy stuff around the edges. Large mirrors, though, don't solve the problems of image blurriness when it comes to atmospheric disturbance. Astronomers use two terms, seeing and transparency, to describe the observing conditions with relation to the atmosphere. Turbulent air causes images to look distorted. Now compare these two images of the same area of sky. The left image was taken from a telescope on the ground. The one on the right was taken by the Hubble in Earth orbit. Since the Hubble orbits above the atmosphere, its images are even better than larger ground-based telescopes. Now compare these images of Jupiter. Can you see that the left image is more blurred and that the colors aren't as distinct? The Hubble image is much clearer. You can see many more individual storm cells. Look at that white stripe where the great red spot is. Can you see those circular white storms? They are invisible in the other photo. This one is magnified even farther by a telescope that orbits Jupiter. This detail could not be seen at all in a ground-based telescope. Only a space telescope could detect this variation in colors in cloud formations. Now take a look at these images. This illustrates another advantage that the Hubble has. Our eyeballs can only see the part of the electromagnetic spectrum that we call visible light. It's really only a very small part of all the radiation that's out there. The Hubble is able to detect not only visible light, but infrared or heat waves. In the visible light image on the left, all you can see is the gas cloud of the Orion Nebula. However, with the infrared camera image on the right, in the same area, we can pick up individual stars forming inside that cloud. Their visible light is not able to penetrate through the cloud, but the heat can. In this way, using different wavelengths of light actually allows us to gain a lot more information than what we can see with our human eyeballs. Here's one more picture comparing two images of a planetary nebula called the Cat's Eye Nebula. From the ground, we can see the dying white dwarf star in the center and the envelope of gas it expelled surrounding it. With the Hubble, though, we can see a much crisper image with a lot more detail. And though ground-based telescopes are limited in what they can see, they're actually getting better. New technology allows us to cancel out some of the effects of atmospheric disturbance. The process is called adaptive optics, and it uses a laser to create an artificial star in the sky. Then, the instrument can see how the fake star is affected by atmospheric disturbance, and use that information to correct the images of real stars. See how much less blurry the corrected image on the right is? Here's an example of how much more detail can be brought out of a planet when correcting for atmospheric disturbance. The first image of Neptune doesn't give us much detail, but we can see much more detail and streaky surface storms that come from the massive winds that occur on Neptune. Different types of telescopes are designed for different purposes. Though the Hubble takes detailed images of very small areas of the sky, other telescopes are used for sky surveys, where they're trying to map huge portions of the sky. Here, this picture shows the entire sky. What we see is actually a bunch of tiny images stuck together. The Gaia telescope is making new and more refined maps like these. Here's an illustration showing you all the different types of electromagnetic radiation, or the different types of light. Visible light that our eyes can detect is roughly in the middle of the spectrum. Radio and infrared waves have too long a wavelength for us to see them. Ultraviolet, X-rays, and gamma rays are too short in wavelength for us to perceive. You can see a scale below showing the relative sizes of the wavelengths. The reason why those different types of waves are important is that each different type of light can give us different information about the object we're looking at. Each one of these narrow strips is a photograph of the exact same thing, looking toward the center of the Milky Way. Look at the third one from the bottom that's labeled optical. This is visible light. There's not a lot to see except a bunch of blackness. This is dust blocking our view of the galactic center. But if you look at the strip right above that, the near infrared, you see a giant bright spot in the middle. That is the heat coming from our galaxy's core. It's not visible in the lower image because the visible light is blocked by dust, but the heat can penetrate through the dust, so we can see it at infrared wavelengths. Each strip corresponds to different wavelengths of light and gives us different information. Here's another image of the electromagnetic spectrum. This one, though, shows the types of waves in increasing order of wavelength instead of decreasing. The first three types here, gamma rays, X-rays, and ultraviolet rays, are blocked by the ozone layer. If you had an X-ray telescope on Earth, it would be worthless. You wouldn't be able to see anything. Other types of waves are blocked too. Infrared waves are heat. Microwaves really shouldn't be listed here, as microwaves are a type of radio wave. Radio waves are the longest waves with the lowest frequency and energy. Remember, this tiny section of visible light is the only type of light that our human eyeballs are sensitive to. You can think of the atmosphere as a house around the planet that has walls and some windows. Certain types of light are let in by the windows, but other types are kept out by the walls. Here you can see that only the visible light and the radio waves can easily penetrate the atmosphere and reach the surface. Infrared light is absorbed by the atmosphere, so infrared telescopes must be placed above the atmosphere. The other types are blocked entirely. To study the types of light that the atmosphere doesn't allow in, you have to use a space telescope. Building and launching telescopes is incredibly expensive. But there are some things you can do with ground-based telescopes to help. First, building them away from cities and high on mountains really helps. It avoids the light pollution associated with electric lights at night and puts the observatory above the clouds and as much of the atmosphere as possible. If your telescope is collecting radio waves, you want them to be far away from cell phone and TV or radio towers. Take a look at how much light pollution affects our ability to see the sky. Just the lights from this neighborhood and one street light makes it very difficult to see many stars at all on the left-hand side. Far out away from cities, many more stars and even the Milky Way itself is visible. Here's another picture of how much light pollution can change in a relatively short period of time. In just 20 years, Tucson, Arizona went from a pretty decent place to set up a telescope to a much more inhospitable location. This shows you just how much damage the atmosphere can do to an image. The first picture shows the stars much larger and blurrier, made fuzzy by atmospheric distortion. In the Hubble photo on the right, you can see the much clearer image. Here are some optical and infrared observatories that exist on the planet. The sites in Chile and Texas and Arizona are good because they have very dry air, not humid like it is here. Hawaii and Chile are even better because these scopes are built on mountains, high above the atmosphere and many weather events. Here's an infrared image showing you a photo taken of a home in infrared light. You can see just how much heat is lost by the house around the windows and doors. This is a similar infrared image, but this time taken of the constellation Orion. The picture on the left is just of the individual stars taken in visible light. But the infrared camera view on the right shows us so much more. We can see huge amounts of heat radiating from the sword region of the constellation, where the Orion Nebula exists. But we can also see a hugely bright area off to the left side. We don't see anything going on in that area of the other photo. That's telling us there's something big going on there, but that we can't see it in visible light. Probably it's being blocked by dust. Radio telescopes actually look a lot like satellite dishes. Sometimes they're a single really large disk like the Arecibo telescope in Puerto Rico. Other times they have many smaller telescopes that work together like the VLA in New Mexico. These telescopes have to have these huge dishes to catch the radio waves because of their long wavelengths. Remember, many types of light must be collected above the atmosphere. Here are images of several space telescopes. The Hubble Space Telescope is in orbit around the Earth, and it's big. It's about the size of a big yellow school bus. There are a variety of different places a telescope can be put into a stable orbit. It's important to know the exact orbits of these objects so that they can never collide. The Chandra X-ray telescope uses a set of mirrors to deflect the X-rays into the detector. X-rays are blocked by the Earth's atmosphere, so X-ray telescopes must be launched into space. Chandra orbits the Earth in an elliptical path that brings it much closer to the Earth at perigee than at apogee. This means it travels very rapidly for a short period of time as it passes Earth, then travels much more slowly for a long time and passing apogee. These are two images taken on the sun. The photo on the right is of the sun in visible light. Notice that it's pretty boring. Not a lot going on, just a few small sunspots. On the left, though, you see a sun that is very active in the X-ray portion of the spectrum. It shows you the location of active storm regions on the surface. This is an image taken in gamma rays. Notice that although it goes generally from more active to less active as you move out from the center, there are a few pockets of intense activity elsewhere. These indicate powerful events that can affect wide regions of space. The Spitzer Space Telescope observed in infrared light. Though the Spitzer telescope is dead and is no longer active, it was collecting heat, and it could image objects with relatively low temperatures. Though stars themselves are very hot, gas clouds can be extremely cold. Look at all the gas that's visible between the arms of this galaxy. The Spitzer telescope orbited the sun, trailing the Earth in Earth's orbit, moving slowly away from the Earth. Hubble, by contrast, orbits the Earth at about 350 miles of altitude. Here is a model of the new James Webb Space Telescope. It replaces the Hubble as NASA's main space telescope. It's named after a former head of NASA. This model of the Webb shows its honeycomb-shaped mirrors over a huge sunshade. Notice just how big this telescope is compared to the people standing around it. It's a lot bigger than school bus-sized Hubble. Webb's mirror is quite large, even compared to Spitzer and the Hubble. It's so big, it actually had to be folded up to fit in the rocket that launched it. It launched in December of 2021, and luckily, it all unfolded properly when it got to its destination. The Webb sits in one of Earth's Lagrange points. There are 5 such stable points where an object can be placed and remain in place due to gravitational forces between the Earth and Sun. The Webb will be at L2. Here you see the Webb at L2. It's much farther out from the Moon, following along with the Earth's orbit, always staying out of the Sun's view. Luckily, everything worked out as planned with the Webb. It is so far away, much farther than the Moon, that we could not send out astronauts to fix it if something went wrong. Here are a few of the first images that Webb took. These gas clouds and galaxies show much more detail than other telescopes can. A couple of other important telescopes are Kepler and TESS. Kepler died at the end of 2018, and TESS launched in 2018. These scopes are or were looking for exoplanets, which are planets that orbit stars other than the Sun. Kepler found thousands of planets outside our own solar system, and TESS will find many more over its lifetime. Remember, visible light is only one part of the electromagnetic spectrum. Each type of light, whether radio, infrared, visible, ultraviolet, X-ray, or gamma ray, has a specific range of wavelengths. Particles of light are called photons. Spectroscopy is an important part of astronomy, and we'll talk about this more extensively in Unit 3. Spectroscopy involves taking the light, breaking it up by wavelength, and analyzing each bit separately. In this image, you can see a spectrum of hydrogen and the spectrum of helium. If you were to look at the sun through a telescope, you'd see that it's a combination of both hydrogen and helium lines. This is how we know what the sun is made of, even though we can't actually go there. When you pass white light through a prism, you get a rainbow. Using a filter, you can separate out the different colors of light based on their wavelength. Blue light has the shortest wavelength, around 4,600 angstroms, and an angstrom is about a 10 billionth of a meter. Using a different filter, you can filter and detect a different type of light. Green has a longer wavelength than blue. Yellow is longer than green. Orange is longer than yellow. And red is the longest of all the colors. Notice that infrared falls after red. Infrared means almost red. On the other side of violet is ultraviolet, meaning very violet. Once we've separated out a star's spectrum, we can determine not only the elements it's made of, but also information about the temperature, mass, density, and magnetic field of the star. But there's something else that's important to know about the pictures you see from these telescopes. Take a look at the colors in this image. Looks like green sky, orangey clouds, and pinkish stars. But are these colors real? We know the colors of the rainbow correspond to waves of different wavelengths. But what would the color of other wavelengths look like if we can't see them? Do X-rays have color? The answer is no, they don't. So if we want an X-ray photo in color, we have to add it artificially. Images taken with a telescope camera are taken at a specific wavelength, so they are monochrome, without color. But since a bunch of black and white pictures are pretty boring, a color is often added to make the picture more attractive and easier to see details. Often, multiple images are added together. Here, 3 different photos were taken, and each one was assigned a different color. A picture was taken in the red part of the spectrum and was colored red. Another in the green part of the spectrum was colored green. And a final picture in the blue part of the spectrum was colored blue. This image of Mars is what we call a true color image, meaning that this picture of Mars looks as Mars would actually look if you went there. But that isn't true in this image. 2 images were taken in the red part of the spectrum, but one was colored red and the other green. A third photo was taken in the green part of the spectrum, then colored blue. The images were then combined to make what is called a false color image. So this image is not what you would see if you could fly to this nebula and look at it directly. If you're imaging outside the range of visible wavelengths, those images are always false color images. Many images will tell you that they are false color, but they won't always do so. If you're looking at a picture that's in ultraviolet, X-rays, or gamma rays, it must be false color.